Hey, what's up, everybody? My name is Terrence Cooksey. I'm a business analyst located in Scottsdale, Arizona. And on this channel, I share in detail all of my portfolio projects with you guys to hopefully get some feedback from you all and also to help out anyone who may be looking for similar solutions to those that I come across in my projects. Go ahead and subscribe if that sounds like something you think you might be interested in. Also, leave a like or a comment if you do appreciate the content. That will help me level up in the YouTube algorithm and hopefully grow my channel. Today we'll be doing a Jupyter notebook walkthrough of my recent exploratory data analysis project that I did in Python. And let's go ahead and jump right into it. Intro. So the first thing we want to do is we want to go ahead and import our libraries. I like to use common naming conventions to keep things simple, and I also see it as best practice across the industry. I want to go ahead and start by importing my pandas module as PD, numpy is NP, matplotlib.pylab is PLT, and I believe PLT is going to stand for PyPlot. So I have another chunk of modules right here from plotly.offline, import plot, iplot, init notebook mode. This is mainly just to ensure that we don't have any issues showing our plotly graphs in our Jupyter notebook. I ran into some issues and this was actually a solution I found. Yeah, make sure you add these modules as well if you're going to be forking this notebook. By the way, the entire notebook will be in the link in the description below. So here we give some brief information on our dataset origins and integrity. I'm not going to go too deep into the introduction. I just want to go ahead and give you guys just a brief synopsis of kind of what the project is about. And this is a real-world dataset from Lyft Bikes and Scooters LLC, which operates the City of Chicago's Divvy bicycle sharing service. The data has been made available by Motivate International Inc. under a license. It's public data that anyone can use to explore how different customer types are using Divvy bicycle sharing services. So introduction. In 2016, Cyclistic launched a successful bike share offering. Since then, the program has grown to a fleet of 5,824 bicycles that are geo-tracked, allowing 24/7 access to thousands of bikes locked into a network of 692 stations across Chicago. I'm a data analyst who joined the marketing analytics team at Cyclistic 6 months ago. Lily Moreno, the director of marketing, believes that company success depends on maximizing annual memberships. Long story short, our team wants to understand how casual riders and annual members use cyclistic bikes differently so that we can form a new marketing strategy to convert casual users into annual members. A little bit on the product. There's 3 different bike types: electric bikes, dock bikes, and classic bikes. Here we have some pricing points: a single ride, a day pass, and annual membership. Electric bikes have premium costs added onto them. There's also premiums and fees around parking, overusage, bike damages, and bike theft. So again, I don't want to get too deep into this stuff. The notebook will be in the description below. So we have 3 questions we want to answer. How do annual members and casual riders use cyclistic bikes differently? Why would casual riders buy cyclistic annual memberships? And how can Cyclistic use digital media to influence casual riders to become members? Now we finally get here to read in data. This is where we import our data. Common naming convention for our data frame variable, pandas.readCSV method. Pass in our path where the data is located. Now we finally got our data. First thing I want to do is update the data types. We run a df.info method to check out the data types. As you can see, we have all objects in float 64s, 6,081,641 rows of data. Entries is rows, and then a total of 12 columns. And currently memory use is at half a gigabyte. So I need to update date times for started at and ended at columns, and categorical D types for biker status and bike type columns. I go ahead and create a dictionary of the new data types that I want, and I use the dictionary to convert specific columns for each new data type that I want. So I use the column as the key, and I'll use the the data type as the value throughout the dictionary. So biker status would be a category, bike type would be a category, so on and so forth. And then we go back to our data frame variable, and we're going to be updating the data types using df.asType, the asType method, and we're going to pass in the dtype dictionary here with the keys and values, and that's going to update our data types here for us. And we're going to see biker status is now category, bike type is now category, started at and ended at columns or date times. Now the data types are updated. I also converted float64 to float32 in attempts to save some memory, and well, it looks like it worked. I optimized down over 150 megabytes of memory. Finally, I can work with the refresh memory for the remainder of the project. It's time for feature understanding. Feature understanding, let's go. Data frame.head 2. This is just me looking at the top of the data frame, just kind of getting a visual of what we're looking at. Feature understanding. During this phase, we get an in-depth understanding of our data through univariate, bivariate, and multivariate analyses. Just as I did with data cleaning, I'll start from left to right but this time with the univariate feature understanding. After I get a summary and understanding of each feature, I'll start to connect the dots. I'll begin seeking correlations within the data from there, 2 to 3 variables at a time in a bivariate and multivariate analysis. Once this is complete, I can move on to the analysis stage where I'll ask questions and make inferences before summarizing my analysis and making recommendations. So here we have the Matplotlib inline. This is another module or package, not sure what you would call it, to prevent issues with visualization showing up in the Jupyter notebook. Univariate analysis of single variables. So now we're in univariate analysis and feature understanding. The first column we're looking at is biker status. Let's get a univariate understanding of the biker status feature. So first we need to get a subset, df underscore bstat. Bstat is short for biker status. So now we got our subset of the biker status series, and now we can go down to begin to describe our data. So we go df_bstat.describe method, and we run the toFrame method as well. So the toFrame function is a function that's used to convert a normal series into a two-dimensional data frame. So it basically takes a column and kind of lays it out in the format of a data frame. At times it makes the series or the data layout a lot easier to see. So I'm going to be using this function here a lot throughout the notebook. So as we describe the biker status series, we can see there's 2 different unique biker status values, which is member and casual riders. And member is the one that appears the most throughout the series at a frequency of 3.6 million times. Now we can get counts. So we use our df_bstat variable .value counts method and toFrame, and that gives us counts of member and casual, how many times members and casuals appear in the series. And you can see again, we see members more so than casuals. plt.style available. Here I was just looking at some different formats. Went ahead and went with the default version, and then I went ahead and went with the Seaborn version. I probably could comment one of these out. Yeah, when you're going over your codes, you see a lot of silly stuff that you may have skipped over or forgot about or just flat out messed up on. But here we go. Matplotlib.rc parameters.update, and we got axis.grid as true, so we're gonna have a grid. So there's gonna be a lot of customization in all my visualizations. So we have axis.grid to true. We have the grid color as Gainsborough, so it's just a really light gray. PLT_RC params axis.face color is gonna be W for white. And now we're gonna plot. We take our data, value counts, and we use just the base python.plot method. And for the kind argument, we're gonna do a bar graph. And this is the custom color I have. And then we go PLT X ticks. Rotation, that's just to flatten out or get the horizontal view of the x-axis labels. PLT.Y label is going to be label count. And then the label pad, I think this is just giving us a little bit of space. 12, font size 15, color grade. Same thing with the X label and the title here, font size, and then PLT show. And you can see we have count of member and casual rides. Members are going over 3.5 million. Casuals are just under 2.5 million. In the frequency bar plot above, we can see member counts breaking above the 3.5 million line, while casual user counts sit just below 2.5 million rides. Annual members account for the majority of the bike rides in the data set. This shows us that annual members potentially ride bikes more often than non-members, who are also known as casual riders. Now we want to get a proportions object. So we got the counts, now we want to get the percentages. So we call this variable dataframe.bikerstatus_prop for proportion, and that's going to be assigned to df.bstat, which is the dot value counts, or that's bstat is actually the series, right? And then we're going to go to a dot value counts. We're going to pass in a normalize argument and set that to true, because that's going to give us percentages. There's an approximate 60-40 ratio split between member and non-member rides in Cyclistic's historical bike share program data. 3.65 million annual membership rides represent 60% of the whole, while 2.42 million casual bike rides constitute the other 40% of that 6.08 million ride count total. Let's graph this. Let's graph this. Put the exclamation point, you have to say it like this. Let's graph this. Visualize proportions. PLT.figure. I commented these things out. These are just like settings that I'll toggle on and off right now for my VS Code format. Create a circle at the center of the plot. We're going to be making a donut chart. So we go my circle will be the variable name, and it's just going to be pyplot.circle, and then we pass in our integer 0, 0, and then 0.63. I think this is the size of it, and then the color is white, and then we go ahead and plot a pie chart behind that, and then that's going to be pyplot.py data frame bstat_prop, and then we pass in our labels, our percentage format, and then I had to tilt this angle so that we can kind of get it going from left to right and starting in the center. Text props, so this is just the font size and the percentage PCT distance. I believe this is the percentage distance. Pyplot.gcf, which is get current figure, and then we take that and we say get the current axis, because we're going to put that figure onto the axis, same axis, and then we use .add artist to add that actual figure, which is my circle, which is again just the circle, not the pie chart. And then we're going to put that on top of, again, the current figure, which is the pie chart. And then we go pyplot.title, and we go ahead and put a title on it, font, change the font size, PLT show, and we have a beautiful donut chart. And we can see casual users account for 39%, 40%, annual members 60%. Our donut chart shows a clear depiction of the approximate 60-40 ratio of member and non-member ride counts. In my opinion, we're doing a wonderful job at Cyclistic, with over half of our warm audience or people who've used our product in the last 12 months having been converted to annual members. That's amazing. Let's see how we can improve that number even more. Now we're on to our next feature, bike type. Let's get a univariate understanding of the bike type feature. DFB type. Again, we're going to pull that Panda series, DFB type.describe, and we're sending that to a data frame format. And here we see there's 3 unique, and again, those are the 3 different bike types: electric bike, dock bike, and classic bike. and electric bike is the most popular. So we're going to do value counts. We got value counts, electric bikes most popular, classic bike second, dock bikes way behind, not really a thing. We're going to go ahead and visualize counts. We're basically repeating the process, as this is another categorical series, so everything's going to be pretty much identical. So now we want to go df btype value counts plot, all the same thing. We're not going to go through. These are all pretty much identical. We have 3 bars here, but it's all the same thing. So it's a close call here between preferences of electric bikes compared to classic bikes. As you can see, they're both pretty close, around 2.5 to 3 million. As we can see here, electric bikes count over 3 million rides, and classic bikes just over 2.5 million, with dock bikes barely charting at less than 250,000 rides. Let's look at some proportions of these values to get a better understanding of this comparison. We're going to get another proportions object, kind of repeating the same thing that we did with the last feature. So this one's going to be called data frame btype underscore prop. Again, the same thing. You can see electric bikes are at 51%, classic bikes at 45%. And same exact thing, visualize the proportions. We're going to go with another donut chart. So percentage of bike types used, and we can see that 51% to 45% to 2.9% ratio split. This data tells us that people predominantly stick between electric and classic bike styles. Let's get a univariate understanding of the hour a day feature. We're going to get a subset df hour of day, assign that to a new variable. Go ahead and describe our data. We see the most popular hour a day is 5 p.m. People like to ride during the evening time or just getting off of work perhaps. There's 24 unique hours, of course, 24 hours in the day. And we're seeing that 5 p.m. pop up 614,000 times. Now we're going to go ahead and get counts, same thing, except we're going to actually run a head function and only get the top 5 hours. So I'm going to be doing a lollipop chart here, and so I think that that's the reason why I'm going to be using a pandas.dataframe method here to go ahead and assign this variable to an actual data frame so that I can use the index for my lollipop chart. So we go down and we say update index to hours for the lollipop chart, right? So we'll go df underscore hour 1, and we'll reset the index in place true to make that permanent. Rename columns. So I'm renaming our columns to equal, and then I have a dictionary here. So for the index column is going to be named hour, and then the hour of day column is going to be named count, because I must be doing some sort of, right, I'm doing a count, value count. So then we go down to df hour.1, and you can see we have the hour and the count. Awesome. So then we want to sort data frame. So we sort values by count, and the axis is 0. Ascending is going to be false, meaning that it's going to be descending, and in place will equal true. And then here we're going to go ahead and plot. We're going to get the hour, the count, orientation will be vertical, line format will be light gray, that's the color of the line. The marker color, the base format, which is the x-axis line pretty much. And then here we just got the title, the label, the y label, the x labels, and we put a grid on it, very, very light, so we can just keep some sort of track since it's so far horizontal. And we can see bike ride counts by hour, 5 p.m., 4 p.m., 6 p.m. Again, 3 to 7 p.m. are the most active times of the day, the least active, of course, the wee hours, midnight to 4 a.m. Appearing at a frequency of 614,999 times in the data set, our lollipop graph tells us that 5 p.m. is the most popular time for bike rides. So we go ahead and get another proportions object. We can see some percentages here with 5 p.m. coming in at 10%, 4 p.m. at 0.08, so on and so forth. So here I kind of found this weird solution of like a proportion bar graph that I was able to create. It was actually really helpful in terms of visualizing what I was trying to visualize. So how did I do it? Here first you can see just our colors here. Then we went ahead and went to pandas.dataframe, and we took our df hour prop variable and we transposed that and we plotted it into a bar graph. Of course, customize our figure size and the width of the bars. Then we did some more customization with the X ticks and the Y label, the title, width and height of the text, and the legend. We added some text here with the 5 p.m. annotation that we got here. We can see the proportion distribution graph I've created. So that's what I call it, a proportion distribution graph I created above. That 5 p.m. is the sweet spot for rides, accounting for over 10% of the ride counts in our data. From midnight to 5 a.m. we see some less popular hours. Let's go ahead and highlight the top third to see what hours throughout the day that users see as the absolute best times to ride cyclistic bikes. And so when we take our df hour.prop proportion and we do a percentage of ride counts from 3 p.m. to 6 p.m. and we take the top 4 and we do a sum and round it to 2, we get around 0.34%, 34% of percentage of ride counts from 3 p.m. to 6 p.m. So a third of the counts sit between 3 p.m. and 6 p.m. And then we'll find the lower extremity and just do .tail6.sum. So I don't know why I put 1 to 4 here .sum. That might be an error, but I did, when I printed it, I said percentage of ride counts from 3 p.m. to 6 p.m. equals, and then I went df hour underscore prop dot head of dot head or dot sum and rounded it by 2. So I'm just adding up the top 4. So I'm not sure what I was doing here. However, it does look like the math is right at 34%. pd.dataframe df underscore hour dot proportion, and then we take the tail of that and we get the from midnight to 5 a.m. and then we go ahead and do a tail 6 and sum that up, and we're gonna see that so from 12 a.m. to 5 a.m. we're only seeing 0.04%, or is that gonna be like 4%? And then we're going to visualize that. So we got our colors, we have an axe here, and we transpose that again and use a stacked, okay, this time we're going to do a stacked bar chart, bar graph, or horizontal bar. And we're going to stack that, and we're going to rotate it 90 degrees to make it horizontal. We have our colors up here. This is the size and the legend. Okay, this is just axes, labels, and ticks. And here we go. So we can see that 34%. Times from afternoon to evening seem to be the most popular time for bike rides. 3 p.m. to 6 p.m. are peak hours for users, accounting for roughly 34% of rides. This means that over a third of the data sits just between 4 hours of the day. As you may expect, the wee hours are the least active times, with ride counts decreasing significantly from 12 a.m. to 5 a.m., making up less than 5% of the ride count distribution by the hour. Next is the day of week feature. Let's get a univariate understanding of the day of week feature. df week is going to be the variable, okay? Same process we're going to describe. We see Saturday is the most frequent day, 7 days a week, so no errors there. We're going to do value counts. Okay, now we're going to go ahead and visualize that. df week.value counts, sort values in ascending order, so from lowest to highest. Then we go ahead and plot that into a horizontal bar graph with the color. And I don't see stacked on here. Not sure if this is another stacked bar graph. Okay, now axes and labels. We did some labels for the containers here, and I used a for loop to do that. You see we're able to get the labels directly on the bars. In order to do that, I had to use a for loop. So we said for I in ax containers, ax dot containers. So ax dot containers is, I believe, containers is an attribute of axes, of the ax, I believe. And that's going to be the iterable. And then I is going to be the item being iterated. Ax dot bar label. And then I, the item, will be iterated right here for every value in ax.containers. There will be a bar label iterated here where you'll have padding to be 20, the label type will be centered, the font size will be 14, the color will be white, and then we have some string formatting. And then, okay, we have another for loop within the for loop. And then for x in I dot data values. For every item in ax containers, each data value will have x, which is here, as the string formatting, which is that comma dot 0 for the data values in the bar labels. So that's how we got the commas and the string formatting of the data values in the ax containers. So I thought that was pretty cool. Although there isn't much of a significant difference in days of the week that users like to ride, we can see that Saturday is the day that users log the most rides. 956,985 rides over the past year. Monday is the least active day of the week for Cyclistic customers. So now we want to get day of week proportions. So we're going to be doing proportions again, this time for the day of week feature. And just some percentages here. Again, we're going to do colors. We have another ax. We're going to do another transpose into a stack bar chart. This time we're going to go vertically, I believe. Right, so we're rotating 90 degrees. Labels, axes, ticks, text, all the regular stuff. Ride count percentage by day of week. So we have 31% of the ride counts are logged through Saturday and Thursday. So just these 2 days of the week account for a third of the rides. So Saturday and Thursday really popular. Saturday and Thursday log the most rides by a day of the week, together making up 31% of the distribution. So now we're on the month feature understanding. We're going to speed this up a little bit, guys. Let's get a univariate understanding of the month feature. So we get a subset. We describe the data once again. July is the most frequent month. Looks like summertime is the best time to ride. Understandably, we get counts. Here we have the months in ascending order, so from lowest to highest. So July is seen the most. December is the lowest, the least appearing month in the data set. Now we're going to go ahead and visualize that. And as you can see, we went ahead and just went with the horizontal bar graph. And again, we did some labels there. And I believe, again, we used the for I and ax containers for loop solution. So we can see July with over 800,000 rides. December, January, February, things slow down a whole bunch, under 200,000 rides. This is a clear case of seasonality in the data. July has the most ride counts, followed by August and June, while December, February, and January have the least amount of logged rides. So we're going to get a proportions object again. We're going to do a proportion of this. So here we want to go ahead and calculate the low season total proportion. So we take df month prop 9 and add that to month prop 10, which is the last 2 months, I believe, and 11. So the worst 3 months, and we're going to add that up and call that our low season. Do the same thing for peak season. And we're going to look at the top half percentile. So we're going to look at the top 50% as well. And then we're going to go ahead and plot out our proportions graph, pretty much the same thing. Yep, another stacked bar graph. Okay. And as you can see, the percentage of rides counts from December through February. Low season is 9.2%. Ride counts from June through August, which is peak season, 39.1%. And the top 50%, is from June through September. Granted, there may be other influential factors contributing to this trend. I think it's a sensible hypothesis to form. Seasonality affects a lot of markets and it's fairly common. So here I have the little entry about some little research I did about seasonality, and we're just going into how that may affect the business of the year. Now on to the start of that, end of that columns. We'll be working with these two features actually in our time series summarization. And for the geospatial longitude and latitude data, we'll be working with these 4 features in our geospatial analysis. So here we are to our geospatial summarization. So we'll start with the latitude and longitudinal data. Let's look at some of our geographical data, get a better understanding of the latitude and longitudinal features. First thing we'll do is we'll make a deep copy of our data frame. When we set the deep argument to true, that just makes the change pretty much permanent into our new data frame variable. We're going to call this df_geo for geospatial. So the first thing I like to do is transform our geographical data from latitude and longitude to something more readily identifiable and easier to work with. If we can access ride distances by mile or kilometers, I think it will be a lot more intuitive. This will help us to be able to derive some actionable insights from this data. So we do a list. We just take these 4 series and we're going to just basically assign a new variable called the geolist because we're going to be zipping these into a list. Lists, plural. Get column that shows the miles traveled for each ride. So the first thing we want to do is import the Haversine module as HS. This is going to be allowing us to work with great circle distance data. So it's just a really amazing formula that allows you to pull and convert and find distances from latitudinal and longitudinal data. So we're going to first create lists, then we're going to use an apply method to pass those into our Haversine formula. So create list of columns to pass into apply method. So df_geo start coordinates, and we're going to call this a start coordinates. And we're going to take a list, and we're going to zip start latitude and start longitude, which is going to be our start coordinates, and we're going to zip that in to a list. So these 2 series will be zipped into a list. It's almost like a single series. So we're taking 2 series and basically combining them into 1 series. And we'll do the same thing with the end coordinates. And we're going to now define our function for our Haversine formula. So we go def for define. Our function is going to be HAV, abbreviation for Haversine, and we're going to have 2 parameters, x and y. We want to return rounded to 2 the HS for the Haversine module dot Haversine method or function, and we're going to say x, y, and then we're going to put the unit as the unit argument to miles, dot miles, and again we're rounding that to 2. That's simple. And then we run function to parse lat long data into miles travel column. So we go df_geo miles traveled, which is going to be the new column we're creating, the new series, and we're going to say df_geo dot apply. We're going to run an apply method. We're going to use a lambda, anonymous lambda x function to go ahead and apply that to the Haversine function. For x, we're going to use our start coordinates. And for the other x, was I supposed to put a y here? I think I was supposed to put a y here. Okay, I see what's going on. So we have the lambda x Haversine, and then we go x parameter by x parameter. And that's because we have the x and y. We have two different parameters for our Haversine function. And so, but lambda is gonna apply those as x for each of these parameters. Start coordinates and end coordinates. And then we go an axis of 1, which I believe refers to the columns. So axis 1 is for columns, axis 0 would be for rows. Okay, and so we run that function. We take the top 5 rows of the DFGO variable, data frame variable, and if we scroll over, we can see, boom, we have a miles traveled column. Yay! Absolutely amazing. We've parsed the latitudinal and longitudinal data into a new column telling us how many miles each biker has traveled from ride start to ride finish. Although this won't tell us the exact distance they've traveled due to the fact that there's no tracking information throughout the entire ride, we do have information telling us the distance from start to end. This is extremely useful information we can use to learn more about user habits. Now we finally got our hands on some numerical data. Let's try some summary statistics on this variable. So finally got some numerical data. Of course, we jumped right into a describe method, and we applied some string formatting here with the decimals, and we can see the average miles traveled is 1.31 miles. Standard deviation is 7 miles, so on and so forth. We do have a 6,000 mile trip here, so that looks like an outlier. So yeah, we say there's some disproportionate outliers values in the miles traveled column, which doesn't sound accurate. We'll dig deeper into this and we start running queries, creating objects to isolate the errors. So we go a miles traveled greater than 10, and then we do a PD set option so we can see the amount of rows we need to see. That just changes the settings of the view of your rows and columns that are returned. And so we see, let's see what we got here. I can see values in the in lat and in long columns of 0. This is almost surely an error because 0 latitude and 0 longitude falls on the equator alongside African countries such as Equatorial Guinea and Liberia. I highly doubt that someone rode a cyclistic bicycle 6,000 miles in a beeline from Chicago to West Africa. I thought that was funny. That was a joke that I told in the middle of a Jupyter notebook. All right, sorry. Probably shouldn't have done that. All jokes aside, an easy way to detect outliers in numerical data is to visualize the variable in a box plot. We'll do this now. So we draw a box plot to visualize outliers. We use the DFGO data frame variable .boxplot. Column equals miles traveled, plt.show, and we can see we're heavily distorted here. Our box plot has been heavily distorted due to the extremity of the dispersion within our array. It's good we caught this outlier prior to doing any further analysis, or else our analysis could have been biased. Outliers can have disproportionate effect on key statistical results, such as the mean, which can result in misleading interpretations. This is why I try to take a technical and structured approach when cleaning my data, moving one column at a time from left to right. In addition to this, even if I miss something while cleaning, I still have a chance to pick up on it soon enough throughout the analysis by starting with the univariate analysis first to detect issues such as these. Though I should have caught this earlier during the cleaning, I'm glad I caught it during analysis. Let's go ahead and count these 6K plus mile errors and see if we can remove them without jeopardizing the integrity of our data any further. So we go to count rows where miles traveled are greater than 10. So then we just run the length, DFGO, we're going to query miles greater than 10, and there's 2,455 rows. Count rows where miles traveled are greater than 20. And there's 14 rows where miles traveled are greater than 20. View rows where miles traveled are greater than 20. So we want to view those rows, so we go ahead and pull those up. And we go ahead and sort those by miles traveled in descending order. And boom, we found the errors. I can see where once we get above 26.27 miles, we begin to see the 6,000 mile error. By sorting in descending order, I can see that at least the first 7 to 10 rows are the only rows with the error. Also, when looking at the starts and endpoint of in-lat and in-long are 0. I'll check the in-lat and in-long columns next. Yeah, we see all these zeros up here around in-lat and in-long. And then they stop somewhere down here. So that's where we're saying 7 to 10 rows. And then, so count rows where the in-lat or in-long value have a value of 0. So view rows where in-lat or in-long have a value of 0. So we pull those up. These are the 8 rows. And we can see each 6,000 mile error has an in-lat and in-long of 0. Seems as though the Haversine formula calculated the distance to the latitude and longitude coordinates of 0. Again, it's unlikely anyone biked that far. Respectively, I'll delete these rows. There are 8 columns total with this error. I'll omit these rows from our data frame now. Go ahead and filter rows where miles traveled are over 100. And then we recount the rows where in-lat or in-long have a value of 0. All rows containing the error have been removed without disrupting the integrity of our data. Great. Now let's continue our summary statistics on the miles traveled column. Average miles that users travel is 1.31 miles. Okay, the furthest distance going to 26 miles, further than 26 miles long, which is more, I guess, logical than 6,000 miles. We see a much tighter standard deviation, surprisingly the same average of 1.31. This is likely due to a small amount of errors there were in comparison to the sample size. However, this does go to show how standard deviation can help detect outliers in data as well, even with only several large outliers. So we do see minimum distances of 0. This may be because bikers are returning bikes to the original station. So we can't necessarily say that those are errors. But now we're going to apply some distributions on this numerical data. So we're going to get a miles traveled object for the plots. We're just going to call that X. So now we're going to do our layout where we have figure and axis and pie plots dot subplots, and we're going to do 1 row and 2 columns. We're going to do our histogram on the left, which is going to be frequency, and our histogram on the right will be proportion. We just do our axis and we establish x0. We're going to do x for our data, our series, and then we're going to customize the bins to go from 0 to 5, and then we'll do a color, and then we'll set the title, some customization on the font, and here we do a numpy arrange function, 0 to 10 counting by 1 for our ax1 bins, and same thing. Okay, here we do some weights with the numpy.1's length x divided by length x. So just a quick formula here for the weights, and we get current axis and use that for the y-axis to set a major formatter for the percent, and pie plot x ticks and arrange, so we have to customize some x ticks, and a lot of customization on this graph to say the least. And we get a miles traveled frequency graph and a proportion graph. And we can see over 50% of the miles traveled happen between 0 and 1 mile. In the histogram subplots above, we can see travel by miles heavily right skewed in both frequency and proportion. Most rides, are over 50% of the rides, seem to fall within 0 to 1 mile range. This is visualized by the first bin and the proportion density histogram to the right. slightly etching the 50% tick. As for the frequency histogram to the left, you can see the 3.03 million rides logged with the 1 mile bend alone again, representing half of the data set, which holds roughly 6 million records. So now we want to look at some coordinates on an interactive map. Visualize the geographical ride location data on a map. So we're going to establish a new data frame variable called data frame lat long. And that's just going to be off the dfgeo data frame variable. And we're just going to query miles traveled greater than 0.01. So where there was some sort of movement tracked. And we're going to sort the values by hour of day in ascending order, descending order. And we're just going to take the top 10,000 of those because this interactive map is fairly heavy on the performance. And so I just actually was, if you're following along with this, I would suggest just do 10,000 at a time, and you can use the head function, the tail function, or you can do different queries, to kind of create different subsets and different angles of the data that you can look at through the map box, unless you have a machine heavy enough to process it all. For me, I was just able to see enough using 10,000 values at a time, and that's how I kind of did that to avoid too many memory issues and not sitting waiting for code chunks to run for too much time. df lat long to go ahead and check out our data frame. As you can see, we have 10,000 row subset. We now have 15 columns as we run a shape attribute on the data frame. Now we want to plot an interactive density map. And so we go px.density underscore map box, which this is, use the lat. We use the nlat and nlong data. So first I looked at the endpoints. And then I think I changed this out and looked at some of the start points as well. And I was just kind of moving around different subsets to kind of get an idea and get a visual of where, a lot of the activity is going on. And spoiler alert, I was not able to really see much difference in activity from casual users in comparison to annual members. So that's just something heads up on. So here we go with our customization of the density map box. And so we're doing a color continuous scale, which is just like the gradient, I think blue Y1 is like a sequential color scale. Range, color, zoom, radius, opacity, these are all customizing what our dots will look like, or our points, if you will. Hover name, hover data, this is what will pop up when we put our cursor or our mouse over the points. So we're going to be showing the biker status, hour of day, bike type. Plotly likes to use dictionaries for a lot of the arguments. Category orders. This is just the order in which the category will appear. Width and height. Map box style, which is the type of map we'll be using and the size. And then we do an update layout, where again we're going to be using a dictionary just for the text and the font. And then we update the margins, just changing the layout, fig.update layout, and fig.show. And here I just did a density map just to kind of show the city of Chicago, show that everything is located like directly in the city of Chicago. And here you can just hover over and see some stuff there. So now we're going to plot actual points. This was actually a density map. This was not the points. Now we're going to plot the actual points. And as you can see, We can zoom in, and right here on the north side of Chicago. And you know, we can filter these out and show only, I don't know where my customizations are at. We can filter these out and show only, here with the legend, only members, or excuse me, only casuals right now. And if we zoom out, you can see there's a lot of activity here in the center. We bring members back. They're pretty much the same in the same place. So there's not a lot of contrast between member and casual activity, as I said. But this is a pretty cool interactive map that I was able to create in Python right here in the Jupyter notebook. So I was happy with that result. And so we see that rides stretch north from Evanston area down to the Blue Island area, from the lakefront west into the Cicero and Elmwood Park areas. Most rides are located in the heart of downtown Chicago, with many points consolidating toward the center loop of the downtown area. The clusters of points disperse to become more spread apart from one another as the rides get further out from the center downtown area. You can see some dispersing there. There's no clear, people that ride far trips over 15 miles tend to stay within a 2 to 3 block radius from the shoreline. Harbors and waterfront areas. This could be due to traffic flow, bike lanes, or just nice views of Lake Michigan. There's no clear distinction between member and casual rider activity that I could pick up on geographically by looking at this map. And now for our time series summarization. So we have so we're going to start a new data frame variable called df time, and we're just selecting our columns we want to include there, and reordering our columns actually. Seeing our ride locations plotted on the map was awesome. Gives me another idea. Was the ride high intensity, low intensity, or moderate intensity? So we're going to just create bins and create some new categories to kind of see if we can get a new column telling us if the ride was long distance, moderate, or nearby, and was the ride high intensity, moderate, or low intensity. So we'll extract the intensity column showing ride intensity intervals first. So we run a query to get the miles traveled that are over 10 miles, rows with rides that lasted over 10 miles long. So we want to view miles traveled longer than 10 miles for the high intensity interval. So we want to find people that rode the bike over 10 miles in under a certain period of time. And that would kind of denote to us that that was an intense ride. So only 2,447 rides went further than 10 miles. This tells me this is definitely going to be on the higher extremity for this data set. I'll look at the length of ride time to get a better understanding of intensity before trying to establish my intervals. So we get rid of the copy of slice warning. Oh, we had a little error popping up there. We had to go to pd.options mode.chain assignment to equal none, so that the slice warning would stop popping up. And then we make a copy of our data frame where we're actually subtracting the ended at and started at times to get a data frame ride time, which is pretty awesome too. So we wanted to look at the length of the ride time to get a better understanding. So we say, we now have a column named ride time, which displays the length of each ride, which displays the length that each ride lasts for by subtracting the ride in from the ride begin to get time delta data. Ooh, so now we got time delta data. Parse ride time in minutes column. So we go df time, data frame variable, ride time minute series we're going to be creating. and we round data frame time by the ride time series into a date time dot seconds, and we divide it by 60. So however many seconds, we're going to divide it by 60, and that's going to give us how many minutes. And then we're going to cast that data type into an integer, and we see we have ride time in minutes, which is awesome. So then we're going to round the ride time. So now we're going to run a describe function on our new ride time column. The average ride time is 16 minutes, and the standard deviation is 29, and the longest ride time is 1400 minutes. It looks like we have a minimum ride time, a value of 0 minutes. This seems inaccurate to me because there's no way a ride can last less than a few minutes. Possible reasons for this could be canceled rides or simple logging issues of Cyclistic's app or bike stations. I'll have to omit these rows from our data set to prevent outliers from distorting statistics and metrics our data shows us. All rows with 0 ride time error have been omitted. We run a new describe function on the data frame. The average ride time is still about 60 minutes long, not much has changed. Showing some variance does exist in ride times. Looks like the dropping the rows didn't affect our statistics too badly, which is a good thing, and increases the likelihood that our previous stats on the other columns are still accurate. Minimum ride time is 1 minute. Someone could technically get on and off a bike unsatisfied with that amount of time, within that amount of time. I'm fine with that value. Longest ride time is 24 minutes. This could be an error as well. Yet it's possible users keep, the longest ride time is 24 hours. So we found an error here. Longest ride time is 24 hours. This could be an error as well, yet it's possible users are keeping the bikes overnight. Let's look at some distributions of ride time. So we get the x1 variable for the minutes object for our ride time plot. So after our distribution of ride time in minutes, you can see the histogram on the right shows that most rides last less than 20 minutes. Right here, things get really heavily skewed to the right. So now we want to view the longest ride times. And we find that there are rides lasting more than 1 day and up to 24 days. This seems like it could be an error, considering this is far too long for any person to ride a bike. However, it's possible that bike rentals are allowed to be rented for longer than 24-hour periods, giving users access to the bikes as if it's their very own. The way the information on the project was conveyed to me, I feel as though that's kind of what was insinuated. So as long as the user is paying for the usage, from a business standpoint, I don't think it's a bad idea, since I think there is an interesting business model. Since I think this is an interesting business model and it fits the data, and this is what I interpreted, I'll go ahead and go along with this theory just for the purpose of this analysis. Therefore, we will not be removing those rows. Now we want to create an object isolating errors. So we go df time, open bracket, df time, ride time greater than 1 day, sorting value by ride time in descending order. And so now we're isolating those errors. We have 186 rows where the ride times last longer than 1 day. And so we continue to isolate those errors. And there are 2,174 rows with ride times longer than 12 hours. Even if these were errors, they won't skew the results as they're minuscule in respect to the size of the data set. Again, we can go with this theory for the analysis regardless, so we'll just leave these rows there. We do notice a miles traveled column. Columns are equal to 0. We find that there are over 307,000 rows where miles traveled are equal to 0. Miles traveled values could possibly be 0 due to riders returning bikes to bike stations. This may not be an error either, so we will not omit these rows either. So now we're going to continue to try to filter for ride intensity intervals, and we'll do a PD settings option to display the max rows to be 50, and we just do some filtering here for rides longer than 2 hours and miles traveled further than 10 miles, and on a classic bike because it really wouldn't matter in terms of an electric bike because you're not really working out that much. So the idea was to kind of figure out if people are using this bike like for exercise, like for intense exercise. That was the idea of trying to find the ride intensity intervals. Most ride times that are under 50 minutes are on the electric bikes. It's hard to tell the intensity. Someone may be exercising on the electric bikes because electric bikes can do most of the cycling for the rider. The classic bike, however, is a way for us to measure actual rider intensity. According to an article on cyclinglevel.com, a good 10-mile cycling time is 32 minutes and 55 seconds for a man and 39 minutes for a woman. This is the average 10-mile time across men and women of all ages. 28 to 37 minutes for ages between 20 and 50 years old are considered to be of the elite class. The clock times we see users cycling 10 miles or more on classic bikes are around 50 minutes or more. So cyclinglevel.com classifies these times as either beginner or novice for both men and women. So this tells me that most users are likely riding cyclistic bikes for just commute purposes or as a hobby or maybe simply for a lighter exercise. So from this insight, we can see there's no need for a ride intensity column. Next, we'll just look at creating the commute distance column, which may prove to be more helpful. So we're going to extract a commute distance column showing ride distance intervals. First, we'll look at miles traveled less than 1 mile. And over 3 million users, or around half of cyclistic bike riders, travel less than a mile while using the service. Then we'll look at users who travel between 1 and 5 miles. And 2.8 million cyclistic users travel between 1 and 0.5 miles. And then we'll look at users that travel over 5 miles. Only 100,000 users have traveled further than 5 miles. So we can see the majority of cyclistic users typically use bikes from within a 5-mile radius. Again, this doesn't detail how far users actually rode the bike, and it only tells us the distance between the 2 points from which they pick the bikes up and drop the bikes off at. So quickly we'll go ahead and form our distance column. So we'll use the pandas.cut function to chop the data into 3 separate bins or levels that will give us a nearby distance, a moderate distance, and a long distance. And we'll use .copy to make that permanent to our series. So our bins will go from 0.01 to 1, negative 0.01 to 1. So from 0 to 1 mile, and from 1 mile to 5 miles. And then a float for infinite, so anything from 5 miles and on. And then our labels, we have our labels for our bins here. Now we have a column showing distance traveled in intervals of nearby distance, moderate distance, and lastly long distance. So now we want to get counts of travel distances. So now we have some counts here. We want to get proportions. We have proportions here. We want to go ahead and visualize those counts. Nearby distance, moderate distance, long distance. And we're going to get proportions of member and casual bikers travel distance and place that in a table. And so we can use the unstack function method to go ahead and place that into a table. So we go dftime.groupby, we group by biker status, casual and member. Then we take the distance column, which will give us these 3 columns. And then we'll do value counts. So we count those and then we normalize those true to get some percentages. And then we'll unstack it to kind of lay it out in a better table format. And then we'll multiply by 100 for the percentage. And we'll do some string formatting, adding a percentage sign on there, and we'll round that to 1 decimal. And so now we can see casual bikers choose to travel a moderate distance 49.4% of the time and a nearby distance 48.6% of the time. These proportions are very close, and I doubt their differences are statistically significant. However, they give us an insight on casual rider preference. As for members, 53% of their rides are at nearby distances and 45% at moderate distance. This means that casual bikers tend to travel a bit further than members. So why do casual bikers travel further than members? That's a question that we need to find out. A reason for this could be that annual membership bikers use Cyclistic on a daily basis, being that they have 24/7 access to the bikes year-round and therefore ride for less time per trip because they generally ride much more frequently than casuals. Since casuals don't ride daily, they could be taking extended trips to get the full enjoyment out of their experience with Cyclistic. This is a hypothesis that we can look into more clues to support during our bivariate and multivariate analysis. For now, we can start our time series data to support our seasonality trend we previously uncovered. So now we're going to make a copy of a data frame variable, and we're going to call this one date index. And we're going to take the date index and set the index to the start of that column in place true, so that'll be permanent. And then we'll go filter for casual rider status subset, in which we'll be filtering just for casual riders for the index, because we're going to be doing a line graph. So this is for our casual user line graph. And then we'll have an annual member line for our line graph as well. So now we want to run aggregation methods on the resampled daytime index data frame. So we're going to resample our data. We're going to set the variable to casual, average miles per day, and that's going to look like the date index for casual users, and it's going to be resampled by days. So for each day, it's basically going to create like a window or like a bin for each day, and it'll just sample it or like group it by each day, and then it's going to aggregate some of these aggregate functions that we can use similar to when we're using a group by. And so we're going to aggregate our data based off of this date index being resampled by a day. We're going to look at biker status, and we're going to get the mode biker status for each day. So whichever biker status pops up the most times for each day, then we're going to get the average miles traveled for each day, the average ride time for each day, and the most frequently appearing day of the week for each day. And we just use anonymous lambda functions to get that done for mode, and dictionary for the aggregate functions themselves. And so now we can go into a filter for member rider status subset. So we're going to be filtering for members now, and just the same thing we did before. And we're also going to be resampling that, because again, this is going to be for our member and our casual users. And I should have brought this up in a little table. I meant to bring this up in a little table so that you guys can kind of see how cool this is and what this kind of does in terms of resampling things into different time frames. But I think I actually do that because I'm going to be creating multiple line graphs, and I think I do that a little bit further down for our other line graphs. Now, so let's go down and check out the graph. So once again, just going to be a lot of customization here. It's going to be Plotly graph. So it's going to be go.figure for the fig. And then we're going to go fig.add trace. We're going to add a trace, which these are actually scatter plots. Go scatter plots, but they're connected through the lines and markers to kind of create a line graph. So X is going to be the index of the casual user average miles per day variable, and we've just plugged the data and miles traveled in for the y-axis. And then for the mode, we're going to be doing lines and markers. For the marker, again, this is a Plotly graph, so you're going to be using dictionaries for a lot of the arguments. And we're going to see size of 2, color. The name is going to be casual. We're just naming the actual line, I think. And then the color and the width of the line. And then we go into our second trace, which is going to be the same thing but for our members. And then we're going to update the layout with the axis title and date, right? Axis title and labels and some customization here. So we have the fig update layout where we create a spike, which is, you're going to see is like a line that kind of scrolls with you as you hover over the line graph and kind of gives you your values and some information to kind of let you know where you're currently at on the graph. So we need to show spikes as true, and it gives a spike thickness, and we use a spike dash. We chose the dot. Looks pretty cool. Spike color, we chose gray, and we want it to be across. So here we need to update x-axis because we actually had a range slider. So we set range slider visible true. We use a dictionary for the buttons list, and we create a button where we count and bends the days, right? Because the step is day, step mode to date. So we're stepping backward by day, and we're doing 14 days and calling that a week. Yeah, I think that's more like bi-weekly or something, or 2 weeks. But 30, so that may be a mistake. So we have 30 days here, stepping by day. We have 30 for the map number for the count. So we're stepping by days. We have 30 for the count. And then for the step is going to be a month, and we have 6 for a 6-month count. And then we have step all, which that's the last button, which will allow you to kind of view the entire graph. So we go fig update layout, and this is the hover distance and the spike distance and the hover mode. So this is just, again, the spikes for when you're hovering over the chart. And fig update layout. This is for the grid on the x-axis. So just some font and color customization. Same thing for the y-axis. Taking off the 0 line. Establishing the margin and that type of thing. And so here's our time series graph, our first time series graph, which is showing by day, as you can see, March 21st, March 22nd, March 23rd, March 24th. So, and then this is our spike line that we were talking about. That gives us kind of a dynamic view as we're going through out the graph, where we can see exact values for each point on the graph. And members and casuals are pretty much neck and neck for average miles traveled daily by biker status. And we have our buttons up here. You can go to day. You want to just look at a day at a time, or a week, or a month. And then you can slide this across, and it'll just give you a month's view of your data. we go to January 1st on the end, it'll probably take us to around December 1st. So it's about a 30-day step. Let's see if the week was incorrect. If we click week, let's see if it gives us 14 days or 7 days. 17, 18, 19, 20, 21, 3, yep. So it looked like it gave us 2 weeks. So I probably should call this a week or 2 weeks. So there's an error for you guys. There's a couple more in there I didn't mention. Didn't want to look like an amateur. Okay, so in the interactive time series chart above, we can see the average miles trending up from March before consolidating around June. So if we go back to all, we can get our whole chart. So from March, we're trending up, and then we start consolidating around June. So right here, we reach basically a lower high right here around June 19th. And then we just kind of start to consolidate, and then we start to decline, probably with this low right here on September 11th, and this lower high right here on September 24th, and then things just kind of go all the way downward. Okay, and let's so then in September we see average miles traveled begin to decline. So I said in September, which was accurate, and around Christmas, we see the worst days of the year before activity begins to reverse and pick up toward the upside again near February. This looks like a case of seasonality. From May to July, we see a steep climb. And so my thoughts are we could promote both preceding peak season and during peak season to capture momentum and enthusiasm amongst local bike adventurers. This could drive up conversions for Cyclistic by the end of the summer. So now we want to run aggregation methods on resample date time index data frame. Again, this time we're going to be resampling by month. So everything is exactly pretty much the same. We're getting the mode biker status, average miles traveled, average ride time, mode day of week. But this time I pulled up a little table so you guys can check it out. And as you can see, we're going by month. So March, April, May, June, July is where they're sampling. And this is just the head. We're going to have all 12 months or 13 months if we were to just not run that head function. So this is just the top 5. And then miles traveled, we have the average miles traveled, we have the average ride time in minutes, and we have the most appearing days of the week for each month. So now we do the same thing for members. As you can see, they actually seem to ride more often during the same months, but they ride more often during the days of the week. So that's an insight right there. Here we go, going down to our monthly graph, monthly line graph. Pretty much the same thing with the customization. And now we can see our big, beautiful line graph of casual and member average miles traveled by month. Okay, same functionality as the last graph. And during the early spring months, we see casual riders traveling further than members on average. Summer months are steady, and even as rides increase overall amongst both groups. So during the early spring months, we see casual riders traveling further than members on average. Summer months are steady. So during the early spring months, we see casual riders traveling further than members on average. Summer months are steady and even as rides increase overall amongst both groups. September once again shows the point of decline for rides overall, where members travel further distance than casual users on average during winter months. So that's an insight. We see members traveling more, a little bit further than casual users during the winter. So now we want to run aggregation methods on resampled daytime index data frame. And so we do pretty much the same thing for member and casual user. And now we have average daily ride time by biker status. So we have miles traveled, now we're looking at ride times. And it looks like members ride longer when looking at daily average ride times. Toward mid-September, we see ride times begin to decrease. And we're just running aggregation, resampling, running aggregation methods again, and plotting our last, I think this is our last line graph showing the average monthly ride time by biker status. This one is really conclusive, showing casual users riding longer periods of time throughout the entire year than annual members. Interestingly enough, we see casual users riding for longer periods of time than members throughout the entire year. This is surprising considering that annual members have access to full membership benefits. This tells me that the annual membership pricing tier possibly doesn't give people the benefits they need to ride as long as they want. It's possible that the membership is simply not designed around allowing longer rides and instead is designed more for commute. This can be a huge deal breaker, ultimately preventing casual bikers from buying annual subscriptions, especially if they like the longer rides. This is a great insight for our time series analysis. Let's move on to bivariate analysis and find some correlations. So we make a copy of our new data frame variable. We're going to call that dfbiv. We're going to run a head function, check it out. So we're going to subset the data set, kind of optimize some performance. And now we're down to 291 megabytes, which is really good. Analyze biker status against bike type counts, bivariate. So we're doing biker first. We're starting off with the first two, which is biker status against bike type. So we just do group by biker status. Then we go dot bike type dot value counts, and we're not going to normalize right now. We're just going to do counts, and we're going to send that to a data frame format, two-dimensional format, and we can see casuals. We can see a clear comparison here. Analyze biker status against bike type. So we'll get a biker status bike type. We'll go dfbiv, group by biker status bike type, but this time we'll normalize, set the normalized argument to true, and now we can get a more telling depiction of the difference in bike type usage amongst the two different biker status values from casual and members. So now we're going to do a quick visualization of this. Okay, and it's just a simple double bar chart showing biker status to bike type. We got casual users here and members here. And it shows that casual riders select electric bikes 16% of the time more than classic bikes. Casual riders only ride dock bikes 7% of the time, and members don't ride them at all. Members choose classic bikes just as often as electric bikes. So members don't show a huge preference. This is not a substantial preference. Here, on the other hand, casuals show a clear preference of electric bikes. And that's the beauty of visualization, because it was kind of hard to see that with just those stacked tables here. But the visualization kind of made that a lot clearer for me to see. In my EDA process, I'm gonna be doing listing insights from the bivariate analysis, some questions, and then answers, just to kind of keep my insights and findings organized and just keep them continually pulling throughout the entire analysis process, so that at the end I can bring them all together and do like a final summarization of my analysis. And we can basically, so that we don't miss any data points or any key insights. So casual riders are willing to pay a premium of $1 plus 25 cents more per minute just to be able to ride electric bikes. If casual riders were more aware of the discounted electric bikes that come with annual subscriptions, they may opt in to pay annually. We should consider marketing campaigns that spread awareness to casual riders about savings on electric bikes and the benefits of electric bikes in general. So, do we want to follow this with a multivariate analysis? Yes, because there's a lot of information there. There's a lot of good key insights there. So we're going to continue to pair this bivariate analysis with some other features and kind of see if we can find even more granular insights. Biker status against miles traveled, and we just run a describe function to get some numerical statistics on this bivariate analysis. And we can see members and casual riders travel the same distance, about 1.3 miles on average. Members max trip distance 26 miles, was 4 miles further than casual users. No questions there, no answers. There's no significant difference. Key takeaways, hypotheses, and suggestions. There's no significant difference in average biking mileage between casual riders and members. And so we won't be following this with the multivariate. Now we're at biker status against hour of day. And we have to unstack and reset an index here. Take this to a pandas data frame. We use a dictionary or a set order according to 12-hour format. So we had to reorder categories here. And then we're going to be resetting the index to the hour of day. So we go pandas data frame. We go our bivariate data. We group by biker status. As you can see, biker status, casual, and member. And we also bring up the hour of day as the values. And then we want to do counts of those hours per day, and we want to normalize those to get the percentage to see how many times those values for each hour of day appear in the data set, and we unstack that and reset the index. And so that gives us a flat table. For each hour of the day, we can see the distribution that each group had, again, throughout the entire day. And so we reshape the data for a group bar graph again. We use the pd.melt method, biker status for hour per day, and then for the ID variables, we're going to be using biker status, and then for the variable names, we're going to be using hour of day, a category called, or a column called new hour of day, and then the value for the value names are going to be percentages. We're basically reshaping this data frame, and we're going to reset the index so that way we have a new index, and then we'll pull up the top 5 values of that data. So now we want to parse the hour data to category data types so that we can order them. So we go here, we go .as type to category. Now we need to set order according to the 12-hour format again. So we have to go to .cat.reorder categories, and then we can order those accordingly. And now we can get proportions and use the pivot function to create a table with the index and set the index to the hour of day, and the columns to be biker status, and the values to be the percentages. So now we can do counts first by going pandas.dataframe and pulling up our bivariate data and grouping by hour of day, and then passing in the biker status and running a value count on biker status, normalizing that, or we're not going to normalize that yet, and we're just going to unstack that, pull out the top 2 rows. Now we can see counts for each hour of day and hour of day ordered in ascending order. And so now we can visualize this, and there was a couple tricks that probably went into visualizing this, but we'll just jump to the chart, the graph, and we can. And we can see from 6 a.m. to 8 a.m. things pick up. 12 a.m. to 4 a.m. casual riders represent more of the small activity happening during midnight compared to members. This shows casual riders ride for late night work hours, nighttime fun, leisure, or maybe nightlife activities, more so than members do. 5 a.m. to 8 a.m. There's an increase in percentage of rides with members. 9 a.m. to 10 a.m. member rides show a drop in activity before picking up again at 10 a.m. That could be like lunchtime. And so some other insights there. But key takeaways, casual members are riding more for leisure and non-commute related reasons. Members are riding mostly for commuting purposes. You guys, I gotta admit, I'm pretty dragged, I can't lie. I think that was an amazing video. There's some more cool stuff left, but a lot of the cool stuff I pretty much got through. A lot of it's gonna be redundant, kind of repetitive, and it's really just going deeper into the analysis process. If you guys are interested in that, a notebook will be linked into the description below. If you appreciated the content, a like or a comment would mean the world to me. If you guys see anything that I can improve on in the project, I would love to hear that and just get some commentary started. If you guys have any questions, please reach out. I'm happy to answer questions and help you guys out. My name is Terrence Cooksey. I also go by Terrence in Data. Thank you guys for tuning in. I'll catch you guys in the next one. Peace. Outro.